Really pleased to introduce my colleague and friend, Michelle Creech-Eakman, to kick us off with that, and we'll go from there.
Mic check work? Okay, great. Great, thank you so much. I want to thank everybody for coming this morning and for the organizers for inviting me. I was a little surprised when Gerard suggested that I was going to condense an entire Michelson summer school of 1 week into 35 minutes, but I'll do my best. This is obviously aimed at the non-expert, and so hopefully the experts will give me a little latitude. I'm a professor of physics at New Mexico Tech, and I'm the project scientist on the Magdalena Ridge Observatory Interferometer. So a brief outline of my talk, I'm going to be talking about why you might want to use interferometry and what exactly it is. I'll go through some of the language and the basic concepts behind it. I will give you some ideas of the types of things that optical and infrared interferometers can measure. So I want to say up front that we're not talking about radio in this case, although there are things that are in common. And then I will briefly go over some of the enabling technologies and give you some pointers for places you can go for more information. So when I start out thinking about astronomy, there are lots of different things that drive what we might want to do as astronomers. And astronomers get together in a room and they hotly argue these axes that I've chosen here. So sensitivity, resolution, and time domain. And you can put different things on them depending on what time period you want to think about and what kinds of sensitivities, for instance, you're interested in. So you can look at telescopes over time and the things that have changed. You can do the same thing on this other axis and think about resolution and what we mean there, what we've been able to do as we grow bigger systems or more complicated systems. You can also think about the time domain and the new exciting things that are sure to come there soon. And so when you look at this, people will start arguing, oh, you left some stuff off, and so you put things like HST and JWST on there, and then you argue, well, is that really more about sensitivity or resolution? And then somebody will point out that I've missed an axis or two, and so there's a whole bunch of other things that you could add: cost, complexity, the wavelength space. What is it that we want to do? So today we're really talking about gains in resolution. And so this is the axis that I'm going to choose to try to show you some of the possibilities. So we're going to start with a really simple picture. Imagine that you've got your own very simple telescope in your backyard. You've got a lens to do the focusing with, and you're going to look at a star that's far away, and you screen an eyepiece something on the back end. The light that's coming off the star is going to come out in spherical waves, but we're far enough away that they'll basically be planar by the time they get to wherever you're located. And there will be a wavelength associated with those waves. There will also be a diameter associated with the lens that you choose for your telescope. And so if you were lucky enough to be in a position where you could get a perfect, what we call diffraction limited image, you would get something called an airy disk. It's a little bit hard to see the levels here in the bright room, but you'll notice that along with the central intensity, there's also a ring, and there's another one if you've got really good eyes. And so you can plot out what that looks like, and you will notice that it goes to a zero, a darkness, right here at 1.22 lambda over d, which is associated with the fact that you've got a spherical aperture, circular aperture. If you were hoping to see two stars, the thing that you had looked at, the two stars' light, whether or not you would actually be able to make them out, would depend on a bunch of different things here. One of them, so I put up a second intensity profile, a secondary disk, will be how far apart they are. Another one will actually depend on the wavelength, and the third, of course, is this diameter of the aperture that you're looking at. And so as they get closer and closer together, you will eventually get to the point where you really can't tell the difference between the airy disk for the single and the airy disk for the binary. And so this is really what we mean by resolution. And these are the two things that I want to track. So I'm going to flip this problem on its head, because you could just say, well, let's go with bigger and bigger diameters. Why don't we do that? And that is one way to do it. But another way is, let's start again. So we've got a star and our wave fronts, and I've changed the labels just a little bit, my circular aperture. If I were imagining the light was coming down from the zenith, and so directly down on the telescope, here's my same intensity pattern, my same airy disk. And maybe you can see the plot a little better now. I want to try something different. I'm going to put a different kind of cover over my aperture. So I'm going to have two smaller apertures now with a distance between them. So I'll label those D and B. And when I do that, what I find is that I actually get this fringe pattern. So underneath the airy disk that we have up above, now I have fringes. And the way the particular fringes will line up is going to depend on the size D, the B, and the wavelength that we're looking at. And so we can write down equations for those kinds of things. And we'll get an intensity pattern here, that's what I've plotted, for the single telescope, which depends on this Bessel function. Not going to give you lots of equations this morning, not enough coffee yet. And our D squared for the size of the diameter of the aperture. But you could also write down the same intensity pattern here for the fringes. And in this case, it will depend on this telescope intensity, but also this varying term here, the cosine, which has got the B and the lambda in it for the baseline separation and the wavelength that you're working at. Okay, so I want to point out one more thing, because I'm going to come back to this. So OPD stands for optical path difference. And we are going to care about this particular zero spot where the fringe is the highest in later parts of the talk. So the clever astronomer says, well, why do I have to use one telescope? Why don't I just take lots of little telescopes and push them apart? And that's the Michelson interferometer. So that's what we do next. You're going to get the same pattern that we got on the previous slide with the fringes. We're going to do the same kinds of things that we just talked about. We're going to track the intensity. We're going to look at the baseline separation between the two telescopes in this case. We're going to look at the telescope diameters. But what this allows us to do is not have to look right up at the zenith any longer. We want to be able to track the stars as they go across the sky. And so we collect the light, and we'll do some magic here, which I'll talk about in a little bit. But the first thing about watching the stars as they go across the sky is to look at this line right here. So as your wavefront comes down from the sky, and think of it as a piece of paper if you wish, it's going to intercept this telescope before it intercepts that telescope. And the amount of time that it takes for the light to intercept this telescope and then that telescope can be calculated. It's just geometric. And so you can look at that as B times the cosine of theta for the angle that you're looking at in the sky and the baseline separation. So you could time this difference. So in interferometry language, we call that the delay. And that's the amount of time that you would like to delay the light that you collect at the first collector until you're able to collect it at the second collector, because you want to put it back together again just like it was up at the zenith. So because of the nature of optical and infrared light, for most of the light that we're talking about, you have to do this in physical space. You can't do this with software. See where I am on time. Okay, so some of the basics now, the kinds of things that we add as complications that we need to be able to track as we're doing this. So in practice, detectors that we're going to use actually measure the power that they receive, and that's related to the intensity of the light, or the E squared that I talked about on the previous slide. So we measure the visibility of our fringes, and we talk about this as the difference in the powers for the max and the min, divided by the sum of the powers, and that gives us a scaling from 0 to 1. So we have visibility here. This is an example of a full visibility or full contrast fringes, and this is very low contrast fringes. Also, we're not looking at one color of light, we're looking at multiple colors of light typically, and so your shortest wavelengths will have closer spacings than the longest wavelengths, but your detector doesn't know the difference between the different colors of light that it's looking at, it's just receiving light. And so when all of that light is piled up on top of each other, you'll notice that at the 0 OPD again, you've got a nice high contrast fringe, but as you go away from there, all of the different colors kind of start to smear together. And this gives us what we call a wave packet for the white light. So This is one of my very favorite slides. I use it in almost every talk I ever give. This is taking your idealized 2-element interferometer and looking at something very simple, a binary star. So hopefully you can see that you've got a bright and a faint star in your binary system. And my simple 2-element interferometer is going to be looking at this whole thing and trying to make a measurement. Now, we can think of breaking down the measurement as a convolution of looking at the bright source plus the faint source and just looking at what the interferometer here receives for each one of those. And you'll notice that we have both a fringe contrast and a particular phase at the 0 path delay, or the 0 OPD, in each of those cases, so that when we add them together, we actually get some result, which is not either one of those, but another answer. Without the presence of the atmosphere, you'd be done. You've encoded the fringes, you've got the information that you need, and so everything is fairly easy. We talk about how the brightness distribution of the sky is related to what we actually measure on the ground through something called the Van Sittert-Zernike theorem. It has several important assumptions buried in it, and we don't have enough time to go through all of them, but it's something that you can look up if you want to understand this better. But one of the things that's really important to point out here is that the phase is as important as the amplitude of the fringes to be able to understand what you're looking at, and that's because these are complex visibilities that we're measuring, and the phase information encodes things about the spatial distribution of what we're looking at in the sky. So because of the Van Sittert-Zernike theorem, we have the ability to take a Fourier transform of our measurements that we make and recover the information, the spatial information of what we're looking at in the sky. And if you knew that you were looking at a binary, this might be enough to actually solve what you want to do. And you could maybe take multiple measurements if you want to figure out the orbit, but then you'd be done with it. It turns out that it's not that simple on the ground. So a brief word about the atmosphere. Those nice planar incoming wave fronts encounter the Earth's atmosphere, which is very turbulent. It has all kinds of eddies in it. It has the ability to do this turbulence at different size scales, at different frequencies. It depends on the wind. It depends on your location. And so we worry about all kinds of different turbulence effects, the Kolmogorov scale, the isoplanatic patch size. And this affects how quickly we have to make our interferometric measurements to actually be able to encode those fringes in the phase that we want. It also, unfortunately, messes up the phase pretty well. It also tells you how expensive your interferometer is going to be. Are we going to add adaptive optics to this thing, or are we going to try to go it without adaptive optics? So to give you a flavor of what this looks like, we have, again, our airy disk. And if you take a very short integration, a speckle, we call it, you'll get this kind of pattern through the atmosphere. And a longer integration, you'll be getting up to the scene limit, which is typically arc seconds in size. So the moon does not have an atmosphere, as we all know. So, but anything that disturbs our wavefront the same way that the atmosphere does may need to be considered in interventions that you do for building an interferometer on the moon. So some more of the basics. I kept telling you that phase thing was important. So the next thing that we learn about here is closure phase. And closure phase is a way to get around the atmosphere. So if we have 3 telescopes now, 3 collectors, and imagine that over one of them you've got a patch of bad air that's not allowing you to make exactly the measurement you want. So you'll have the intrinsic phase that you measure at each one of those, and then plus an atmospheric term between each pair of telescopes when you make the fringes. Turns out if you add all 3 of these together, all the atmospheric terms end up dropping out, and you get this thing that we call a closure phase. Now this is an oversimplification in algebra, but it's the basic conceptual idea. So this allows us to have phase information that's uncorrupted by the individual telescope-dependent phase errors. It's also extraordinarily sensitive to asymmetric features, and so it gives us a very powerful constraint on our image reconstruction that we would like to do most of the time with interferometers. Imaging is one of the things you're interested in. And it turns out that closure phase is very critical for several techniques that we want to do. So one of the things to point out, though, is that when you have multiple telescopes and not just 3, with 3 telescopes, you've got 3 Fourier phases, 1 closing triangle, 1 independent closure phase, and you get 33% of the phase information. So as you add more and more telescopes, you're recovering more and more of the phase information, and we can count how many independent closure phases we have based on simple statistics. So over here is an example of Keck aperture masking images shown reduced with and without closure phase. So this is without the closure phase, you get this kind of result. And when you actually put the phase back in, you get what we expect is the more realistic result. All right, a little bit more of the basics. Signal to noise for an interferometer depends on the square root of the number of photons and the visibility that you measure. So it turns out that when I'm giving you an example, I stole this off the Chara website, of a 3 milliarc second and a 1 milliarc second size star. Here's the rubric for milliarc seconds. And if you imagine that you've got telescopes separated by about 50-meter baselines for these, then on the 1 milliarc second star, you've got pretty high visibility for all three. But on the 3 milliarc second size star, when you get out to the longest baseline, you're starting to be around zero visibility, and it's very hard to make the measurement. So we do a trick that we call baseline bootstrapping, where we build up a long baseline of intermediate baselines, where on the intermediate baselines we've got high visibility, and we're able to maintain the measurements and phase up our array. So this is something that we want to consider, I think, as we're looking at things that we might want to do on the moon. There's an analogous wavelength bootstrapping argument that can be made. And one of the last of my basic slides is fringe tracking. And fringe tracking is really the heart of the matter when you're doing interferometry. If you don't have the fringes, you're not making your measurement. So we look at that wave packet again, and this time this one's encoded in blue and red. So we call the red part of the wave packet the group delay, and the blue part in this case is the fringe phase. And I've tried to put a red line on there for you for the zero OPD again. If we do something called phase tracking, we're trying to stay as close to the zero OPD location as we can as we watch the fringes. It may actually be required for certain types of techniques that we want to use in interferometry. When we do the group delay tracking, we're more interested in just keeping track of where this envelope is and chasing it as the atmosphere, in the case of on the Earth, is pushing it around, or various things in your interferometer. So we do this by having these delay line things that I haven't talked about yet connected in hard real time, which means typically faster than the atmosphere changes, so milliseconds are faster than milliseconds, with the detector that's looking at the fringes at the same time. There's a very nice calculation that was done by Charlie Towns in the Michelson Summer School first book from 1999 for the cutoff where the difference between where you can do the homodyne technique and the heterodyne technique. I'm not going to talk about that more than this little bit right here. The homodyne technique is when you put the fringes directly on the detector or on a beam splitter, for instance. The heterodyne technique is like radio, where you're able to use a laser to encode with the fringes so that you can do everything post-processing in software. And the tipping point is somewhere around 10 microns for room temperature. So these are actual fringes, group delay fringes for fringe tracking that were taken with the Coast interferometer about 25 years ago that was in the Michelson book, and they took cuts through various places to show you what this group delay envelope looks like, so you get a feel for what it is that we're going for. So how are you going to measure it? The keys are measuring the visibility, amplitude, and the phase of the target that you're looking at in the sky. The ability to calibrate the measurements is critical. The calibration tells you how far from ideal your interferometer is performing. And remember, we've only got 0 to 1 on that visibility, so you don't have a lot of range. This can unfortunately change on fairly short time scales because we have Earth-based systems that have atmospheres above them and all kinds of things shaking and moving around and heat and all kinds of things. So what types of measurements can actually be made? These are the ones I'm going to go through quickly. A couple of slides on each one. How am I doing on time? 10. Okay, we can do this in 10. All right, imaging, spectroscopy, differential phase astrometry, and nulling. All right, so imaging, start with. We're all kind of addicted to images. We all carry around cell phones and take pictures of things all the time. Imaging interferometry is really the measurement of many visibility, amplitudes, and closure phases, ideally as many as you can get on non-redundant baselines. in order to reproduce a complex astronomical image that you see in the sky. So the projected baseline, I'm going to jump down to these pictures for a second, is what it looks like if you were sitting in the star's perspective looking back down at the Earth. And depending on where the star is located, so this is some Chara data directly overhead, alpha Cep, or off at an angle, alpha Ophiuchus, you'll get a different projected baseline, so you'll get different types of coverage. The MRO interferometer, the layout of the telescopes is in an equilateral Y, which is supposed to give us a good synthesized image. Think of synthesized image as the size of the telescope I'm trying to make with my system. And so building up your telescope with a large number of baselines being swept out relies on this notion of the Earth actually moving around. I wanted to note this because aperture synthesis may be a little bit more difficult on the Moon. This is what you can do with aperture synthesis. This is a simulation that was done by one of the professors at New Mexico Tech with a person at Georgia State and a person at Cambridge on Betelgeuse. So this is about 4 hours of data taken on Betelgeuse in the future someday with the MRO interferometer. So this gives you an idea of the visibility amplitudes, the closure phase data, and the baselines that will be swept out in about 4 hours. Okay. Spectroscopy, and I'm going to put differential phase in here with spectroscopy. Doing any kind of spectroscopic interferometry really requires that you have enough photons so that you can actually do some spectral dispersion with the light. And so there are things that you can do when you're designing your interferometer to make that easier. You can separate your fringe tracking and your science combiners so that you're actually doing two different tasks on two different instruments. You can try to go for bright targets. And if there's anything that you can do to integrate long as possible, then that will also help with the problem. So I'm giving you a very heuristic example here of if you think about a star plus a cool planet next to it and you measure it at some particular wavelength, you might notice that the photocenter, if you didn't know the planet was there, would be offset from the center of the star. And so there would be a differential phase signature looking at this wavelength than either at a different wavelength or when there is no planet present. So this is what we call differential phase measurements. Unfortunately, I don't really see a lot of these being taken by our community, or at least they're not pointed out. So I found a paper, thanks to the Chara folks, that was done by Milan et al. In 2012, showing, looking at a disk and that was in rotation and looking at the differential phase signature across the disk as a very sensitive way to measure the motion of the disk. So with very good precision on your closure phase, you can detect photocenter changes, or you can go to different wavelengths and do the same thing. Astrometry. Astrometry requires making a very good phase measurement at two locations in the sky, usually at the same time. This is how the gravity experiment worked that looked at the black hole at the center of the Milky Way. And this picture up here is to talk about isoplaneticism, or anisoplaneticism. If you're not looking through the same piece of sky above your telescopes, you're going to end up with phase changes that at some point you can no longer track. And so we talk mainly about narrow angle astrometry here. The way that we overcame this with the PTI system, which was a demonstrator for the Keck interferometer, was with what we called a dual star feed, where we actually duplicate our beams all the way through the system, and then we make measurements simultaneously on two different detectors, and we switch back and forth between the bright and the faint star, all the while having what we call a constant term metrology system on, so that we can actually make these measurements through the isoplanetic patch and pull out the phase differences. Wide-angle astrometry with a highly calibrated system might be possible without doing these redundant baselines. This is what NPOI was working on for many years. And there are different tricks for that. So these are just some examples of the VLTI Prima instruments so that you don't just see cartoon drawings, but actual idea of what these instruments look like. Nulling was something that I got to participate in at Keck. The concept was first developed by Bracewell, and it's analogous to coronagraphy. So we all kind of carry around our own coronagraph whenever we want to look at something near the sun, and we put our hand up in the way. And it's the same kind of idea, only we do it in phase. So what you want to do is very carefully control the phase in one arm. You add a pi phase shift so that you put the bright thing in the dark part of the fringe at that 0 OPD, and then hopefully the thing that you're looking for is in the bright part of the fringe and you can pick it out. But it depends on well-placed companions and getting the geometry right for the wavelengths and the baseline separations. So it's challenging for a bunch of different reasons. Star exoplanet systems are probably easier to measure at longer wavelengths because the contrast between the star and the exoplanet is less. You want to have stable deep nulls, but you also want them to be over a broad band pass, and so that can be optically challenging when you go to the mid-infrared, and the calibration techniques are very intricate for this. So this was the Keck Interferometer Nulling beam combiner, and just one arm of it in the lab. It was a modified Mach-Zehnder beam combiner. So this was the beam combiner that sat after about 35 optics in the Keck beam train. All right, so some of the technologies, enabling technologies that you'll hear about this week that we need to talk about. One of them is the delay line. The delay line is kind of an optical trombone, if you will. It's a cat's eye retroreflector system where the light comes in from the telescope, bounces off a primary, secondary, back to the primary, and then it goes back to the beam combiner. It takes care of the sidereal position of your target in the sky, usually with wheels on a rail, and it also can do a little bit of extra tracking via a voice coil to follow some of those fringes. Remember, this is the hard real-time system that talks to the fringe tracker, so it talks very quickly. The length of the track that you've got it running on actually determines how much of the sky you can observe. So if you don't have a very long track, then you have to either add more delay lines or fixed mirrors in the system so that you can track across more of the sky. There are really only two designs that have been employed in working interferometers today. Almost everybody uses the JPL. So JPL, PTI, Chara all use the same design that was introduced here at JPL. VLTI has a slightly different design, but you can see many things in common. And then MROI up here, these are the conceptual drawings for the MROI trolley. It's very hard to see it because it's all encased in carbon fiber, and so it's hard to get good baby pictures for you guys, but I probably can dig some up if you're interested. Okay, beam combiners. You want to make the interference fringes either on a beam splitter, which just means a piece of glass that's got some AR coatings on it to split the light up, or directly on the detector itself. So you can use bulk optics or more recently integrated photonics in the optical and near infrared to do this. There are different schemes to encode and measure the fringes for the applications. So you can do things like play with the spacing of the beams that are coming in so that you can tell the difference between the different beams on your detector and where the fringes are actually coming from. Because this step is always done after the delay compensation has been implemented, these are all very geometric looking things. They have to have very closely controlled distances in the systems. And because this also often includes many optics and little tiny detectors that are the size of a postage stamp, the beams are also very small. So this is a drawing of the Coast 4-way bulk optics beam combiner, and this is the drawing of the Pioneer photonic combiner, which literally looks just like this on the photonic chip. Beam combiners can also be used in different ways, different schemes. So this is a nearest neighbor scheme, and this is the all-in-one scheme, where you're only looking at fringes, in this case, between neighboring telescopes, that baseline bootstrapping thing again. The all-in-one scheme works really well when you're trying to put science together on your detector, and you want to only have to buy one detector instead of multiple detectors. And so there's lots of preferences here, signal-to-noise considerations, physical space, wavelengths that you're going to be working at, and cost. So this is the MROI, nearest neighbors 10-way beam combiner that's in the lab at New Mexico Tech, and this is the old Coast beam combiner for 4. Part of the reason I wanted to point this one out is it's optically contacted, so they made all of the pieces of glass very precisely, and then when they touch them together, they molecularly bonded, and it stays together forever, no glue. So it's kind of cool. We don't use that too much anymore. So last step is the detectors. You can have the Saphira here is the one that many of us have in our labs today. You could also have a linear detector. One of the issues is that you want to be able to read the detectors out very, very quickly. And so having too much detector real estate, which is unusual for astronomers, we usually want bigger and bigger detectors, actually works against you. So you want smaller detectors often so that you can read them quickly. Again, this is about the coherence time of the atmosphere and the light that you're trying to detect. So there are advantages to going smaller. When you want to go into the infrared, you actually have to be able to either you buy a package system or you make a custom system. And often in the infrared, you have to cool these systems with either liquid nitrogen or liquid helium in the mid-infrared in order to get them to work at the wavelengths that you're interested in. This will be an interesting challenge on the moon, depending on where we would want to put an interferometer because the temperatures are going to swing quite a bit. All right, so back to the beginning of what we were thinking about. Let's imagine we're going to build a house. Everybody has their own favorite things they want on their house. They want walls, a roof, the foundation, doors, power, water, HVAC. You have critical rooms. You have specialty rooms. You have all kinds of other considerations. If you're building your house on the cliff by the Pacific Ocean, you're going to have extra special considerations you have to worry about. So we want to build an optical interferometer. We need light collectors, beam transport, delay compensation metrology to know where everything is sitting, beam combiners and detectors, software control, lots of automation on the moon. And then depending on the particular science that we come up with this week, we're going to have different kinds of science features that will drive different things we need to add. And we probably don't need to worry about the atmosphere, but we may have to worry about other kinds of vibrations or other things that will disturb our system. So I made 2 QR codes for you guys last night in case you want to download either David Buscher's Practical Optical Interferometry book from a few years ago or the Principles of Long Baseline Stellar Interferometry from the course notes for the Michelson program. Born and Wolf is also very useful. And the websites for all of our interferometers that are still in existence out there have lots of good information as well. There are 2, there's an article and a simulation I added. And thank you again to the KISS organizers and all the people who've trained me over the years.